My name's Ash Lyons. Join me as I try and figure out what quantum science is really all about. Welcome to Cracking Quantum. First guest, second time recording, because I knew something was going to go wrong.
It has to.
It has to.
That's the law of science as well.
I'm just thankful that you are still here in the country, because you're leaving in like a few days. Like, we'll get to this in a second.
Yeah, I'm in high demand.
That seems like a really mean joke for anyone listening that doesn't know you.
Yeah, I know.
So I'm here with Dr. Sam Nerenberg, who, as we were just discussing like a few minutes ago, doesn't usually go by Samuel, just Sam. So Sam Nerenberg. Sam studied at University of Arizona, where he did his PhD as well. Came over to Glasgow in 2020 as a research associate, where he's been working as part of the Extreme Light Research Group, which is also the group that I work in. So me and Sam know each other really quite well. And he has just accepted a new position over at ICFO, which is the Institute of Photonic Sciences in Barcelona. So yeah, you're literally moving. We're on Tuesday now. You're moving Sunday, right?
Yeah, absolutely. It's it's a bit overwhelming, but I think everything's in hand, and I'm really looking forward to going to a new research institute and just seeing how things are done there, what's different, soaking up all the knowledge. And one of the great things about sort of going to different institutes isn't just the people you work directly with, but there'll be a whole different milieu of research groups surrounding you as well. So there's going to be new things to sort of learn from surrounding me as well, which is amazing. Like you're going somewhere where they might have completely different themes, completely different priorities in terms of their research, and it'll be great to soak all that up along with some sun.
Yeah, that's maybe one of the things that people don't realize who aren't working within academia is that, well, not every university or research institution is doing anywhere near the same thing. Like you can have physics departments across the country or internationally, they'll have completely different specializations. And even within the same field, the nature of their research could be completely different.
Yeah, absolutely. And I mean, even say from group to group, like I'm moving over to this group because I'm interested in optical and optical quantum computing. And my work here has been mostly over the last year or two in optical computing and optical quantum computing. But, the rest of the themes in the group have a lot to do with neurophotonics, brain imaging, brain sensing, fluorescence lifetime imaging, right? But this group I'm going into now, even though they also have a theme in optical computing, most of their background is in like material science, quantum key distribution, communication techniques, with some overlap with like imaging through scattering media and ghost imaging and the like. But even though I'm moving to do similar research, the surrounding research within the group is a completely different set of expertise, and I mean I'm really looking forward to soaking that up as well.
Yeah, and this is one of the things that always comes across when people are building their careers within academia, is trying to go to different places to learn from all these different environments, literally just by being around people who are doing something that's slightly different from you. You pick up a lot of additional expertise.
Yeah,
it's something that I've been really bad at. I basically stayed in the same place throughout my career, but as part of that, I've also had the opportunity to start exploring different fields within that same research environment. So I've been lucky in that way that I've been able to build it up in for a slightly different route.
Absolutely, your work is very broad, and I think I think something that's underappreciated in science is people think that the really valuable stuff you learn as you go is like, oh, I'm doing my research and I'm deriving these equations and I get these big equations and like that's the sort of like stuff I take with me in my career. It's like, well, yeah, those big concepts are important, but I think the real valuable stuff, what experience really grants you, is when you go to these different places, people have different heuristics. They have different ways of almost like skipping past the really making it. You need to think through problems deeply, but when you have enough experience, you have these rules of thumb that allow you to very quickly come to conclusions or very quickly solve problems within your field. And when you find experts in different fields, they have different heuristics. And by sort of building up, like you're sort of keeping a bunch of those in your pocket, that's how you really get experience. That's how you really become a good laboratory scientist, a good, I'm sure theoreticians have their heuristics as well, like, I don't know, tricks for solving integrals or stuff like that. Who knows what they do in there? They're all in their offices working away. What do they do? We don't know.
I've got planned one of the first episodes that I want to do is grabbing one of the theorists that we've got here and literally asking him that exact question. What do you do all day?
Yeah, so what is it so you get paid? We're both physicists, but what do you do? Yeah, that's a good call. Let me know when you get the answer. I'll tune into the podcast.
Anyway, come back to you. So you are, let's say, very definitely an experimental physicist. And
Yes.
like you say, your expertise is in optics and going into quantum technologies as well.
Absolutely. I went to a very specialized center for optical sciences and optical physics for my undergrad and PhD in the University of Arizona Optical Sciences Center. And it was a very hands-on program. And when I did my PhD, now it was a bit of a departure from my undergrad optics in that I worked with what are called Bose-Einstein condensates, which are a type of quantum matter wave. And basically, this is when you cool down matter to such a degree that the constituents delocalize and behave like light. So you have a gas of atoms that acts like light. We won't touch on that, but that exists. And these are very involved experiments. So I'd say a Bose-Einstein condensation experiment is about the most complicated experiment you could expect one person to feasibly operate. They're usually manned by 3, 5, or 10 people. But yeah, they're very involved experiments, and I spent about 5.5 years running one of those labs and performing experiments in quantum turbulence in Bose-Einstein condensates. And so that's my background. And then coming here, my expertise with optics in terms of building large setups, knowing how to image things because BECs, you have to build microscopes to look at them. Knowing how to work with lasers and all these sorts of things were very helpful. Even though the experiments weren't as, say, expansive, the expertise granted by me or to me through that work was really helpful for coming to here and then being able to soak up a lot of the techniques that you guys use and are experts in here as well.
Yeah, and you really touched on something there, which is really important for understanding what these kind of experiments look like, both in terms of optics and in terms of the quantum technology as well.
Yeah.
You really get the full scale of these complicated systems that, like you said, take like 10 people to run, all the way down to the kind of optics that I usually mess around with. I think a lot of people probably don't realize how simple the setups can look like for some of these quantum experiments using light. Like, let's say you want to generate an entangled pair of photons. The actual way that you generate them just looks like I take a laser and I shine it into a chunk of crystal and out pops my entangled photons. The physics behind it is complicated, but the actual experiment looks quite simple.
Absolutely. But, I wouldn't sell yourself short. I've seen some of your experiments and they are quite complicated. But you're right. On the other hand, you have some that look deceptively simple. And I think the big difference between quantum technologies using atoms, using matter, and quantum technologies using light, and sort of right now, their scalability. Of course, people are doing amazing work like we talked about earlier with atoms on chips, so miniaturizing that. But the problem is that, the advantage of using light is that it doesn't interact that much with this environment. Versus atoms are always bouncing off things, absorbing photons. And so the amount of infrastructure you need to isolate matter from its environment to a degree where you can control it at the quantum scale and observe quantum effects is a much different scale than the amount of infrastructure you need to isolate light from its environment, because light is relative. Basically, you just need to make sure that the right wavelength is getting to your detector and you're not getting the overhead lights hitting your detector. Photons tend not to interact that strongly with things. And so while these experiments look simple, they're deceptively difficult because I'm sure, as you know, entanglement is very delicate and things need to be very precisely aligned and very precisely timed. And not only that, even if the experiment is relatively simple, then a lot of the complexity happens on the back end when you're actually trying to extract information from the data. So it's one thing to get raw data. It's another thing to use mathematics, use statistics, use, say, machine learning to pull out the information about what you're trying to measure from it. And that's where a lot of the cleverness comes into play. You have a setup that's got, a few components, but somehow the essence of what you're trying to measure is imprinted in the raw data at the output, and then you need to extract that.
Yeah, a lot of the time when people talk about using optics for let's say testing quantum theories, it's just that it's an excellent test bed to play around with new ideas, new ways to use concepts like entanglement and superposition, but it suffers a little bit in terms of its scalability. Yes. Because that's how you end up with these really horrible experiments that take loads of people to run and like constantly need maintenance, which obviously isn't going to be feasible if you want to try and employ this for something like quantum computing, for example. So you touched on your interest in optical quantum computing. What do those kind of experiments look like?
So again, those experiments are deceptively simple. And that was sort of the point of the work I was trying to do with our PhD student, Oliver, was to come up with a scheme for quantum computing in a very restricted sense. It was actually quantum machine learning, where we were trying to create a system that could be used for some interesting quantum tasks that was dead simple to build, that we could build in the lab with off-the-shelf components that pretty much any lab would have access to. And so this experiment really just looks like a normal laser, and that laser gets directed onto what we call a spatial light modulator, which is a special kind of mirror that can imprint information in a light field. And we imprint, data that we want to do some learning on, and we just send that into an optical, a normal optical fiber, but one that can support many different fields at the same time. And the light bounces around in there and interferes with itself, and then it comes out photon by photon at the other side, and we can use a special camera to count the number of photons that come out at a given time and see which pixels they arrive on, and the different arrangements of photon arrivals on the different pixels contains a processed version of the information, which we can then use some very simple mathematics to translate into a prediction from machine learning, or a function that we want to enact on our initial data that we've encoded. So it seems very simple, but the sort of technology that enables it and the concept behind the physics behind it are actually quite deep, and there's been quite a lot of engineering that's gone into both of those.
So what would you say is the magic quantum ingredient there? Because you talk about this as being like a form of quantum machine learning. It's got to be different from conventional machine learning that we do all the time now anyway. So what's the bit there which is the quantum thing that makes all this happen?
Absolutely. Good question. So there's probably, I would say, two bits that make this quantum. One is that the light field itself is quantum, and so you can imprint quantum information on it, and then through certain kinds of interferences inside the optical fiber, or what we call linear optical network you choose to send it through, the interferences will perform quantum operations on that data. But the real necessary ingredient at the output is what we call photon number resolving detection. So this is the ability to distinguish, to not only be able to detect a single photon, but to be able to distinguish between the presence of 0 photons, 1 photons, 2 photons, 1 photon, 2 photons, 3 photons, 4 photons, any number, a certain number of photons. So not just being able to say if there is a photon or not, but how many actually arrived. And the reason is because the space of different states, basically different photon arrangements among the pixels that allows us to access, grows exponentially with the number of photons and the number of pixels. And so whereas if we were just using classical detection, we would only have a limited number of dimensions in our space to look at our data in, basically however many pixels for instance, we decided to use. When we use photon number resolved, we have as many, we have a certain number of pixels, but then every possible arrangement of a certain number of photons among them. And that space is so much bigger, and that's absolutely vital for the kind of machine learning that we're using. In this kind of machine learning called reservoir computing is what allows us to create such a simple system using physical optical components to do the computing.
There's a really nice parallel in what you said in comparing it to what we would usually think of as quantum computing. Because this is not conventional quantum computing. This is something which is kind of like its own little breed of things around machine learning, right?
Yeah, it's sort of like the difference between like an analog computer, right? A little circuit that does one operation versus a fully digital, fully universal processor, like you might find in your computer.
Yeah, and then this parallel with quantum computing that I kind of had in my head as you were saying all of this really goes down to the example that we usually give is one classical bit of information is, well, it's one bit of information. It's binary. It's either 0 or 1. And the thing that makes a quantum computer more powerful is that you can have not just a 0 or 1 outcome, but you can have some mixture of them, some superposition between these two possible measurements that you can have.
Mm-hmm.
And that's what allows, again, it's all based around the idea of quantum interference, and that allows you to more densely code information in the calculation that you're doing.
Absolutely. The space of states, right? If you have a bit, it has, state 1 or 0, whereas we know a qubit lives in some higher dimensional space until we measure it. But you're able to encode information in some higher dimensional space. And when you have more qubits, the ways they interact give you an even higher dimensional space that you can encode and manipulate information in. And so you have this ability to manipulate and work with a huge amount of data with a relatively small number of physical constituents.
I don't want to go too far down the quantum computing route, because I've got some people in mind who are, let's say, the real quantum computing experts to talk to at a later date.
Absolutely. I would agree with that. I do a very specific thing, and there are people who will be able to talk in a lot of detail about the literature and modern techniques of quantum computing. What I do is a very specific, I think very cool, but yeah, a very sort of niche aspect of quantum computing.
So let's go all the way down to the other end of the scale and the kind of things that you've worked on there, because this is still like relatively complex in terms of the experiment and the data processing that you're doing. What's the simplest experiment that you've worked on?
Well, so as far as experimental setups, I think I know where you're leading to here. The simplest experiment as far as the setup was trying to transmit light through the adult human head. However, counterintuitively, that might be the single most difficult experiment I've ever worked on, both emotionally and scientifically. Yeah, to get light through the adult human head, you really just had a few components. You had a laser that provided pulsed light for reasons we can discuss in a minute. That went in one side of the head. You had a detector that had single photon sensitivity. It could also tell us the precise time a photon arrived. And this was important. The single photon sensitivity is important because it's so hard to get light through the adult human head. There's so much scattering, so much attenuation that we would start out with about 1 trillion photons per second and get on average 1 photon per second, maybe even less. And then, you have a dark box to make sure, because you have such low light levels, that you have to make sure that no extraneous light gets to the detector. And then we had a sort of collection system, so something that could take a relatively large area of that light might be exiting from and guide it to the relatively small area of a detector, because unfortunately, quantum single photon detectors are usually quite small. And so with those are the major components, and it sounds pretty simple, laser on one side of the head, collection and detector on the other side, and then a really dark box. But in fact, this was an incredibly challenging experiment that required not only a huge amount of very, very specific engineering to make sure that we were as dark as possible, so there was no extraneous light, to make sure that we were collecting as much light as we possibly could from the head to make sure there was no light leakage from one side of the head to the other that would give us a false signal, to then extract from a very noisy signal, right? Because the number of the amount of electrical fluctuations in the detector was about 15 false counts per second, whereas our signal was maybe 1 photon per second, extracting that very weak signal from that very noisy signal. So all aspects of this experiment, except for the setup, were incredibly complex. In the setup, even though there were a few components, itself was complex in the engineering and considerations that had to go into it. And that is one of the things about these quantum experiments is, again, as we said before, they're deceptively simple, because even though you might not need a lot of components, the quantum nature is very delicate. You have to be very careful that you're getting what you think you're getting and not some sort of extraneous effect.
Obviously, quite a lot of effort went into trying to get light through the adult human head. Haven't really touched on why you want to do that.
Yeah, well, I asked myself that question quite a lot over the years. No, so there's a field right now that's very active. I wouldn't say it's huge, but it's very active and has pulled in quite a lot of interest, both from academia and industry. And I think, the general public, when they hear about this, are very excited, which is optical brain imaging. So we know that brain imaging is very important to detect disease, to understand how the brain works, to maybe look into things like how could we learn better, what happens in our brains when X, what is the correlation between, sort of mind state X and brain state Y. These are questions that are very important of general interest, but we can normally only investigate them with an MRI machine. And MRI machines are expensive, right? Very few people have access to them. They're bulky, so you can't walk around with one. They restrict you to being inside them. You can't move around while you're getting an MRI. There's all sorts of disadvantages to this sort of investigation only being able to be done with MRI. But if we could instead use light, right, where laser diodes are relatively cheap, single photon detectors now are relatively cheap. They're also relatively small. We can package them with integrated electronics. We could maybe make a hat that would send light into the brain through, non-invasively, so through the scalp, through the hair, through the skull, into the brain, and then measure the light that comes back. And that light would contain information about, say, the blood flow inside the brain. And we know that blood flow is correlated to neural activity. And so there's a whole field called functional near-infrared spectroscopy, FNIRS, where they are trying to replace, or at least, if not replace, get similar information from light as with MRI. However, due to how attenuating, basically how quickly traveling through head matter dims light, these systems, even at the state of the art, are only able to probe about 4 centimeters from from the scalp. So really, they can only reach the outermost layer of the brain, which is fine because that's where a lot of the heavy lifting goes as far as processing, sensory information. That's where a lot of that happens. But what they're missing is the white matter on the inside of the brain, which is which they talk about as like the superhighway. That's how all of the different areas of the brain connect. There's a lot going on there that we don't know about and we'd like to know about. But in addition, beyond sort of trying to extend the reach of optical brain imaging to deeper inside the brain, strokes, so health, being able to look at what might be going wrong with the brain, right? So if you look at what's important after someone has, say, had a stroke or a brain injury that could have resulted in a bleed, within minutes, it's important to know whether there's a bleed or a blockage, because irreversible brain damage can happen very quickly. And if you apply the wrong treatment, so for a blockage, if you apply a blood thickener, so a clotting agent, or for a bleed, if you accidentally apply a blood thinner, you can make things much worse very rapidly. Whereas if you apply the correct treatment, then you can maybe save someone from getting brain damage or from dying.
And obviously, if this is like a matter of minutes,
A
you're
matter
not
of-
going to get someone to an MRI machine in a couple of minutes, but you can make these combinations of these pulsed lasers and these single photon detectors so small that it becomes an easily wearable device that you could just have in the back of an ambulance, for example.
Exactly. Yeah, exactly. So the idea there is that you make life-saving brain imaging technology available in the back of an ambulance, so that someone, as soon as they have a problem, can be diagnosed and given the proper treatment. And if you can do that, if you can make that wearable, if you make that affordable, if you can make it, implementable in a reasonable amount of time, well, you're saving lives all over the world.
So same kind of question as I was asking before about the quantum machine learning that you're talking about. What's the magic quantum ingredient that actually makes that work?
Well, as with a lot of these questions, I think you definitely know the answer to this one, but I like that you're allowing me to answer it. So the magic quantum ingredient here, I would say, is the ability to time single photons. So to be able to know when a single photon has arrived relative to the pulse that generated it. And in order to do this, we have something called time-correlated single photon counting, where we basically have a very accurate stopwatch where the arrival of a photon detector starts the stopwatch, and then the arrival of a pulse from the laser stops it. So if the laser is pulsing extremely regularly, it acts like a ruler in time that allows us to say when that photon arrived relative to a pulse. And what this tells us is basically we can see how much the pulse has stretched going through a medium like the human brain. You can imagine when the light goes into the brain, it bounces around quite a lot, and photons take different paths, and these different paths take different amount of times to reach the detector. And then a pulse which starts out as a millionth of a billionth of a second long then becomes maybe a billionth of a second long, which is quite a lot of stretching. But the exact shape of that pulse is affected by the absorption and the scattering of the medium. So we can tell a lot about what's going on inside the brain by looking at the shape of the pulse coming out. And so we can tell, is there too much blood? Is there not enough blood? And the ability to time single photons very accurately allows us to make these measurements.
You touched on like just how quickly these timing mechanisms work, but just to kind of put this in perspective, what you're looking at is how far light is traveling essentially in a certain amount of time. So if you take the speed of light, that's 300 million meters per second. To put it into, let's say, a more day-to-day perspective, that's about 30 centimeters or a foot in 1 billionth of a second. And when you're looking at how much these pulses stretch and change shape, that's actually on an even faster time scale than that. That's maybe like 10, 20 times faster. You're actually recording when these photons are arriving. So this is insanely quick.
Yeah, absolutely. It's incredible the level of precision we have in measuring light, but other quantum phenomena as well. And I think people a lot of times think that quantum is this sort of airy-fairy sort of imprecise science, and it couldn't be further from the truth. The absolute most precise things you can imagine, most precise measurements you can imagine making, are due to our ability to manipulate and measure quantum systems. I think I'm probably going to get this wrong, but LIGO, the giant interferometer that was able to detect gravitational waves, if I remember right, the level of precision they were able to achieve was something like being able to measure a nucleus in a football field. Is that right? Did you hear this?
I didn't know it in that perspective, but
Okay.
Yeah, it's crazy sensitive.
I don't know if I'm wrong there, but it was something really incredible like that.
And the way that the LIGO is working now, I mean, initially when it was doing the first gravitational wave detections, this was really, really precisely, mostly classical engineering, as it was a classical light interferometer. Whereas now because it's got to that stage of doing everything perfectly, it's actually utilizing some of these quantum effects to push that even further to get
Absolutely.
even more sensitivity, which is amazing. It's a huge achievement in what we've managed to do as a society in terms of quantum research.
Absolutely. And I think this is a good example of when, research into something which seems very fundamental, like measuring gravitational waves, besides scientists, people might say, who cares? Why are we putting money into that? Well, the techniques developed to solve the problems that were very, massive problems in trying to achieve this fundamental research have now had knock-on effects over all of quantum science. So the field of quantum information science, in many ways, in its modern form, was developed in order to solve the problems in LIGO of how do they get more accurate measurements when they need something so accurate that even the pressure of photons hitting their mirrors is creating too much noise for them to achieve the measurements they need. And then people like Carl Caves came up with the idea of getting below the standard quantum limit of measurement by using things like squeeze states. And now those concepts have taken on a life of their own and are being employed all over quantum technologies, all over the world, enabling things like better LiDAR, better scanning technologies, enabling things like quantum computing. It's really incredible, and I think it's a really great case as to why we should care about the research that's going on in these big fundamental projects, not just the output of the project itself, but the techniques that are developed in order to solve these monumental technological problems and how they benefit society.
So, you are infamous in our office for telling the worst possible jokes imaginable. You're just cracking them out all the time. So now's an excellent chance to get one recorded forever. Give us your best joke.
Best joke or worst joke?
I'll take either.
Okay, well, it's hard to really choose one because I love them all so much. But I will tell you one that I recently made up, which I think is wonderful. Other people may have other opinions, but not all opinions are equally valid, as we know in science. So here's the joke. What is Dracula's favorite beer?
Go on.
Budweiser.
That's worse than I thought it was going to be.
It's pretty bad.
Yeah.
Would you like to know my favorite science fact?
Definitely.
Okay. Here's what so again, a lot of good science facts out there. I think this is the best one. Do you know the proper scientific name for the Western lowland gorilla?
I have no idea.
It's gorilla.
It's good to keep it simple, I guess.
Yeah.
It's memorable.
They knew what they were doing.
But if there's other gorillas, they're going to feel left out as not being the gorilla now.
Well, that is a problem. I think we have to find that this is another fundamental research problem we need to tackle. How do we make all gorillas feel equally included in scientific research?
Anyway, thank you so much for your time, Sam. It's been a fantastic discussion, and best of luck in Barcelona. I hope it really goes well.
Thanks, Ash, and hopefully next time I see you, it'll be in the sun.
You've reached the end of the podcast, which probably means that you enjoyed what you're listening to. So please don't forget to like, follow, subscribe, and share this podcast series as much as you can. The more you do those things, the better this podcast is going to be. Don't forget, you can always contact me by email at ash@crackingquantum.co.uk. And please join me again for another episode of Cracking Quantum.